Я радий вітати нашу колегу і чудову науковицю з Middleton State University, професор, а також директор центру QRISE, Quantum Research Interdisciplinary Science and Education Center. Ганна Терлецька, прошу розповісти про success story з Америки. Ми саме знаходимося в спеціальній кімнаті, вона має назву, як ви бачите, Window on America Center. І ви бачите Капітолій. Що ж, тоді з віконця, будь ласка, розповість.
Добре. Дякую, дуже дякую вам за запрошення. Дякую Андрію Сотнікову і Філіпу Кузнєцову за те, що ви робите. Я не знаю, як ви це робите, але ви робите велику справу, і я сподіваюся, учні і студенти це цінують, тому що це дуже важкий час, і робити таку велику науку, і також створювати нові програми, це зовсім нелегко, тому я вас вітаю і маю за велику честь співпрацювати з вами, а також бути з вами разом зараз в Харкові virtually. Сьогодні я вам розкажу про наш досвід будування квантових програм з нуля, насправді. І напевно, ви побачите певні особливості, що схожі особливості в наших програмах, тому я вважаю, така співпраця і обмін досвідом, і можливостями, обміном студентів і науковців – це теж дуже корисно для обох сторін, і є що повчитися з обох сторін, і будемо раді, якщо хтось відгукнеться при подальшій співпраці. Зараз, з вашого дозволу, я перейду на англійську мову. Тобто, я хочу спочатку, я представлю себе. So, I am Associate Professor of Physics in Middle Tennessee State University. This is a map of United States. This is Tennessee. So, we are physically in a geographical center of Tennessee. We have this boring monument to this. But in the center of Tennessee, you have Nashville. You probably have heard about Nashville country music, or what's her name? Taylor Swift, Dolly Parton, and Oprah Winfrey. They all are related to Nashville. But another big treasure of Tennessee is Oak Ridge National Lab. This is a world-known research facility. During the Manhattan Project, it was the center of first operational nuclear reactor in the United States. And for a long time also it has been the home for the world's largest supercomputer. We are always competing with Argonne National Lab, who has the largest supercomputer. And now Oak Ridge National Lab is the home of one of 5 Department of Energy quantum centers. So we are very fortunate to have it here in Tennessee. And I will show you why having national labs, it's like Institute of Research, for example, big Institute of Research in Ukraine is very important. So I would like, because this is an evening session, so I look at the program and I decided maybe my talk would be interesting from perspective, kind of give a bigger perspective of today's day, what you have learned, but also to give you some perspective what is awaiting for you tomorrow and other days. So I hope this will be helpful. Especially now in Tennessee, but also across United States, in different states, we are hearing quantum everywhere. So this is our Governor Lee. So each state has a governor, and this is during this annual state address, he's talking about quantum computing. In fact, he declared Tennessee-wide quantum initiative, committing $20 million to build quantum technologies and workforce development in Tennessee. And we believe this is just the beginning. So next year we will have elections, and our current senator is heavily investing in quantum in the White House. So hopefully more investment from government will come to Tennessee. And this is a news announcement from National Lab. So Oak Ridge last fall secured $125 million a quantum center. That's the second renewal of the center. And here at MTSU, in my institution, we launched QRISE, Quantum Research Interdisciplinary Science and Education Center, on a Halloween, actually. And last fall, a big quantum computing company, IonQ, announced investment on $22 million in a new office in downtown Chattanooga, also in Tennessee. And just yesterday, the major business magazine of United States, the Wall Street Journal, has a news article on 2 or 3 pages talking about how quantum computing works and why this is important, right? So you learn about quantum from government to national labs, academia, industry, and public. So it's literally everywhere. And when these all entities are talking about quantum or some common topic, it means something, right? And what it means to us is something fundamental is changing, and we all have to pay attention to this. It's not surprising, right? You probably have heard already that we live in the era of second quantum revolutions, right? So quantum are bringing new technologies. And just based on the history of human civilization, we know that invention of new technologies always lead to societal changes, right? Invention of steam engine was not just invention of machine, it led to the Industrial Revolution. Electricity was not just about bringing electric bulbs, right? It totally modernized our life. And internet was not just about connecting two computers. It changed how it brought informational revolution, right? And changed the way we educate, the way we do research, the way we do business, the way we go to the doctors, even the way we do wars, unfortunately, right now, right? And now we are at the edge of quantum technologies. So quantum have already left the just basic research labs, and they are entering our society. And it's really not the question if quantum will matter. It's really a question when and who will be ready to participate in this technology. And we know from the history, those who start early, they have more benefits later. So I think it's great that in Kharkiv you have this great opportunities to start early and to get involved from high schoolers to undergraduate and even graduate program, and get involved in research as well as training. And I mentioned to you Tennessee, but it's not just Tennessee or United States matter. There is really global efforts, or maybe global, sometimes collaboration, sometimes competition in quantum. So there is this graph shows, I think they will be updating, this is from Curica company. I think they're updating this graph every 2 years or every year, but it shows that global efforts worldwide are already $42 billion. And you can see that major countries or across the globe, including China, United States, and Europe, they are investing heavily in quantum. Like European Union has European Quantum Flagship with 10 billion investment in quantum. In United States, we have around 5 billion. So we will have another reinvestment in quantum, hopefully soon. So it's a really global matter. At the same time, on the right graph here, I show the infographics from this is McKinsey company. This is a famous firm in United States which are investigating different markets, and their prediction is that quantum technologies will have a huge impact on economies across the globe, estimating by 2035 from of millions to hundreds of billion dollars. Okay, but what is most important for us, a new generation like students like you, is that these new technologies and quantum economy is bringing new careers and new jobs. So, for example, in United States, it has been predicted that by 2035, we will have around 1 million job openings. And what is also interesting, that it's not just for physics majors, it's for all STEM majors. So science, technology, engineering, math. And so there are opportunities for many people to be involved. And I'll talk about this later. So more about this later. So I mentioned government investing in quantum, but also industry are investing in quantum. And it's probably one of the few times in the history of science when academia, national labs, government, and industries are heavily involved in working together or independently, but at least on the same topic. So industry are doing great research on quantum themselves, and they're driving the field to the progress. So big industry giants like IBM, Google, Amazon, Microsoft, they all have quantum programs. Also, we have new quantum companies like IonQ, Honeywell, D-Waves, which emerge as part of the quantum edge or quantum revolution. These companies are different depending on the products they produce. It can be software developers, right, which provide software for quantum. It can be hardware and software systems, or it can be the whole loop, right, depending on the industry vision. And we are very fortunate to have one in Ukraine. I think this is well-known company, HiQ. They have people know them across the globe, and I think you are specifically fortunate to have Mykola Maximenko given a panel or talk. I think tomorrow or some other day. So if you have, please ask questions. Look for opportunities to be involved. What skills you need to have, what training, because that's a really unique opportunity for you guys. So this was the introduction, but before I continue, I would like to put the take-home message. I would like to start with the end. My take-home message is that quantum is not just physics anymore. We mentioned this before. It's becoming technology, industry, and careers. So for the second part of my talk, I would like to go quickly to give some short overview, generic overview of what quantum technologies are going to be are enabling now due to the progress in science. And then we will go to the careers. So what new quantum technologies are at the table now, and we call it quantum 2.0 technologies, because we know quantum is not a new science, right? We just celebrated 100 years of quantum physics. But what is new is that now we are at the stage of engineering and science where we are using quantum effects like superposition, entanglement, interference to build technology which utilizes effects. And these technologies are, roughly speaking, grouped in 4 areas, like quantum computing. That's what the school is about. Quantum communication and cryptography, quantum simulation, and quantum sensing. And I would like to give a very short overview on each of them because I think there are many opportunities for you to not only get trained in these technologies, but also do research in them. And I look at the programs that will be CERN school together. So there are also opportunities to do some internships or exchange of students or researchers. So I think it's important for you to be aware of those. So let me start with quantum computing. So if you look at this picture, right, we already use a lot of computers in our life, right? We work on our laptops, we sleep with a cell phone, we go everywhere with a cell phone, we read books and write on tablets, we go to Oak Ridge to run calculation on frontiers. We basically drive computers now to work. And so these computers are coming in different forms, sizes, and shapes. So my question to you, if we have already so many computers, why do we need another type of the computers, right? Because also there has been a huge hype in the community that my next computer will be a quantum computer. So the question is, why do we need these computers, new computers? And do you individually really need a quantum computer to sit on your desk? So I have this question for you. So why do we need quantum computers? And I start like with the quantum computers will eventually, and I want you to finish the sentence. And I give you A, B, C, D options. So I wonder, what do you think should be the best answer? Anyone?
I think is to do computations that are too difficult for classical computers.
Wonderful. That's wonderful. Thank you. So I just wanted to make sure that there is no misconception that classical computers are bad, right? Well, they are good, right? They do solve and solve many day-to-day problems, and they serve they accomplish tasks that we need for our everyday life, and they do amazing jobs, right? However, there are types of problems that I will mention today that are they are intractable for classical computers, and no matter how big they are, right? So having new types of computers can help us to solve the problems that classical computers might not be able to solve. And you have had introductory lecture today about the difference about how to encode information on classical computers or binary bits, and on quantum computer where you use the concept of superposition and you encode it through qubits, and that gives the advantage of encoding a lot of information simultaneously, and you can design algorithms which can potentially solve the problems faster, more efficiently than classical computers. And as we know, these quantum computers come in different flavors and different different platforms, including based on superconducting circuits like Google, IBM, Amazon, or the ones that came to Tennessee recently, IonQ and Quantinuum, which are built on trapped ions. They have less number of qubits, but they're saying they are more stable and less noise prone. Or you can have like companies like QERA from Harvard, which use neutral atoms to build quantum computers. They have different modalities. They have cons and pros. Which one is going to win? We don't know, but maybe they'll just serve different purposes, right? But again, the message is that quantum computers are not simply a better version of today's computers. They are totally different. They represent fundamentally new paradigm of processing information, and they have potential to solve certain type of problems important for humankind. right? That's why there is so much interest in these quantum computers. And these problems include optimization problems, material science, chemistry, discovering new drugs, cybersecurity, logistic problems in finance, and etc. And during the schools, you will get familiar with different aspects of these problems, right? You will learn from Dr. Christina Hnatenko and I think Teslenko about different algorithms, quantum advantage. You will learn about application of quantum computing to solving certain real-life problems, probably from HiQ and other talks. So stay tuned. But let me go very quickly so some overview of the types of problems that quantum computers can help us, right? One of the problems is optimization problem, and it's basically finding the best solution out of all possible solutions. And one of the challenges with this is that when you're searching for this optimal solution, you have to go through each solution in your data set, right? And when your data set or number of variables is big, then it takes a lot of time to solve this, right? So let's just look at simple example. We have a P table, and we have to sit two people. So of course, I took your favorite professors here. You sit them, Dr. Sotnikov on the left and Dr. Kuznetsov on the right, but you can switch them, right? So there are two ways you can sit two people at the table. Easy, right? Then let's go to three people, right? So how many ways are you gonna to sit three people at the table? So I'll give you 3 seconds to think.
6.
6, right? So we went from 2 people, 2 options, we increase by 1 more person, and you have 6 options, right? So number option increased by 2, and if you invite to your home 10 guests, which is not many, right? Imagine Ukrainian weddings, we have 200 people at the table. So, but with 10 people, you have 3.6 million ways to seat the guests at the table, right? So the problem becomes it's n factorial, right? This is the combination you have. So the problem of just sitting, finding the optimal sitting of people at the table becomes exponentially hard, right? And this is the type of problems where quantum computers can be helpful. And this was just a toy example, right? Just a simple example to entertain you. But these optimization problems are actually real in real life, right? We have logistics problem when you want to put as much cargo in your airplane as possible and make sure that the plane is safe to travel. You have a logistics problem. We order things here on Amazon, so you want goods to be delivered as fast as possible with minimum cost to the company, right? Cost, time, length of the route, human, all cost real money. So optimization problems are everywhere in our life, and solving them efficiently using quantum computers can be a way to save a lot of money. And that's why, not surprisingly, quantum companies, for example, like IonQ, this is a recent article, in April 2025, but they partner with Airbus and BMW to use quantum computers for optimization problem like in aircraft loading. So if you have a chance, you can read this up. So I mentioned to you optimization problem as one of the problems that quantum computers can be useful for. Another types of problem, and I think this is very dear to my research as well, Dr. Sotnikov's research, is material modeling and chemical simulations. And this goes back historically to Richard Feynman's famous quote that nature is not classical, damn it, and if you want to make a simulation of nature, you would better make it quantum mechanical. So this is basically since 1981, that quote launched the concept of quantum computing. So if you want to simulate quantum nature, you have to do it on a quantum machines, which have quantum nature of that. And just to demonstrate you why, so here's an example of caffeine molecule, which is a small molecule, has only 24 atoms. But if you want to model this with all the bonds, all the interaction on the classical computers, you will need 10 to the 48 bits, right? So imagine that big number, right? On a quantum computer, to encode exactly the same information, you will need 100 qubits, right? So quantum computers, again, offer potential exponential speed up for a number of problems that one can simulate for material design, chemistry, pharmaceutical application. And again, industry are exploring this. This is a paper from old paper from IonQ and Hyundai, and this is IBM and I think it's Mercedes-Benz, basically, a study on using quantum computers to simulate batteries, lithium batteries, because batteries are about 40% cost of electric vehicles, and we need batteries to, the goal is to design better batteries which improve charge cycle, right? Durability of the battery, capacity of the battery, and safety of batteries. So this is very relevant research to modern life, where things are shifting to EV cars. Another direction which so I mentioned quantum computing. Now I want to talk to a little bit about another quantum technologies like quantum cybersecurity and quantum networking. And this is the type of research where actually governments all across the globe are very much interested, because it's about security issues. Okay, so as of 2025, well, we had like 8 billion people worldwide, but around 5.45 billion, or 5.5, let's say, were online, connected through the internet, right? That's a lot of people online, and they transfer a lot of enormous amount of data, right? It's banking data, medical records, educational data, private data, transactions data, right? And we want all this information to be secure. So encryption keeps this information secure, but of course you have hackers. So in classical cryptography, the information that we send through the internet, well, typically uses mostly RSA security protocol, which encodes the message information you want to send using the key, and you need to have the key to decipher this. But the idea of this RSA security method is that it uses so-called one-way function. So it's a mathematical function which is easy to do in one way, but it's hard to do the inverse problem. An example of this is multiplication of the big prime numbers. So for example, to create this classical key, which is 21,879,983,000, to create this, you just multiply these two big prime numbers, right? This is how you generate this classical key. But to break this key, you will have to find these numbers, right? To do inverse of the problem and find what is P and Q which generated this key. So on classical computers, multiplication of such big prime numbers, factorization of these big prime numbers is not a simple problem, and it takes like hundreds or thousand years to break. However, there is quantum algorithm for factorization problem by Peter Shor, which can factor big numbers in exponentially faster than on classical computers. However, for this to happen, you need to have a big number of good qubits, like from 1,000 to million good qubits. So far we are safe. However, the progress is moving very fast, so we have to be ready. So NIST, this is National Institute of Standards in Maryland. In 2024, they accepted new post-quantum cryptography classical protocols, and now starting 2026, they are becoming implemented all across United States. Now, next thing that I would like to talk about is that, and this is something that we also do in Oak Ridge and now trying to pursue in other areas of Tennessee, is building quantum network and quantum communication. Specifically, one of the things that we have been doing in our region of Tennessee is instead of sending using classical key distribution, we start to do experiments on using quantum key distribution. And this is really built on quantum mechanical principles of sending and receiving information. So specifically, you have two different nodes, and you send quantum information in the form of you send your qubit, but basically you send qubit in certain polarization of light, and this type of quantum key distribution is fundamentally different, first of all, from classical one, and plus, whenever you have any eavesdropper, it can be revealed automatically, because when you measure quantum state, you change it, right? And I think tomorrow you will have a very nice lecture by Kirill Snezhko, where he talks about polarization. So I hope probably he will mention about how it can be used in quantum key distribution, where they look at polarization of the qubit to detect whether there was an eavesdropper. So there has been some experiments on quantum networking design in Oak Ridge National Lab. There was a quantum network between several buildings in Oak Ridge around 300-meter distance, as well in Chattanooga between two campuses. So now next thing that they're trying to do is to connect different cities through the quantum network. Is a challenging problem because quantum signal is weak. It's prudent to noise, so you need some so-called repeaters. It's not an easy problem to solve, but at least this is the direction that Oak Ridge is thinking about. And I also want to mention the final quantum technology that has been already explored a lot and probably is one of the most mature quantum technologies, quantum sensing. So these are devices, sensors devices, which are built on quantum identities, right? This can be atoms, it can be NV centers, or like another identities, quantum identities, and we use them already in different applications. For example, here on the top, I'm showing you a squid sensors, right? By the way, in these sensors, quantum sensors are extremely sensitive. They have such a precision that no classical sensors can achieve, and they can be applied to medical application, defense, submarine detection, and etc. And so, for example, here we have a squid sensor that can detect tiny changes in the magnetic field in the head, and this is potentially used, for example, to detect brain tumor in early stages. We already all use MRIs, right, which is based on superconducting magnets. Turns out recently there was an article about how you can use NV centers to detect a virus in your body, because it changes the magnetic moment of the NV center, and that changes magnetization, and you can measure this very precisely, and then know if the system has a virus or not. And of course, quantum sensing is relevant for defense systems, and that's relevant for the for Department of Defense. So I mentioned to you that quantum technologies, that quantum is bringing new technologies and industries. And now next logical step, which is related to our school, is careers, right? And I will talk about US quantum workforce. So in United States, we have a huge challenge. This is the MIT report on job market in United States over the last 20 years, right? And what we see is that starting 2016-17, there has been huge growth of the number of jobs which have quantum in their description. However, only 1/3 of jobs have been filled because there are not enough trained people with quantum skills. The same has been reported in President's report on quantum information science strategic planning. And it was again emphasized, basically every report in the United States is emphasizing that the field is currently creating more jobs that we have trained people. And these jobs are in academia, in university, in industry, national labs, and even government, right, across the whole sector. So we need people with different skills. So if you like to work in quantum jobs, so you can work as a researcher, a quantum researcher, very likely you will need to have PhD, and you can work in national lab as a university faculty, or you can go and work on industry, right? If you want to work as a quantum software developer, get a computer science degree, math background, even physics degree, right, and become an algorithm developer. You're learning Qiskit in this school. That's the skills that are needed for this type of jobs. You can be a quantum engineer. You can build hardware, and or you can do some quantum application. Remember, I mentioned like INQ study, IBM studies. This is quantum application, what quantum application jobs would require to do. On this graph on the right, I am showing also that you don't have to have PhD in quantum. It really depends on the type of jobs you want to do in quantum. For example, if you want to be a technician, so this violet curve shows that you need mostly bachelor degree or master degree or some associate degrees like community college degree. It's PTU, I think, in Ukrainian. But if you want to do an error correction scientist, you're a green line, right? You need to have a PhD. But the bottom line is that, like in United States, I think there are more jobs which require less PhD. So 50% of the jobs don't require PhD. With bachelor degree and master degree, taking introduction to quantum computing classes, maybe having quantum optics. If you have master, it's even more opportunities, but you can find a job. And one more thing that I want to emphasize, especially here in the United States, we are emphasizing that quantum jobs are not just for physics majors only. It's becoming very interdisciplinary. We need people from engineering, from computer science, chemistry, math departments. So because quantum is really by nature interdisciplinary. So there is room for everyone in this field. Also, I want to mention this was an article last year, and I went inside and looked for the salaries of these jobs. So these are very well paid jobs, but it's more like quantum algorithm developers, more like programming skills. So why I'm bringing this up? Because the skills you're learning in Kharkiv school this week, like how to use Qiskit, Python, how to develop different algorithms, these are relevant for this type of jobs. And if you are interested in getting internships or real jobs, there is a very nice website, QAD Collaborative, or Consortium, sorry, and it has jobs all across the world in academia, national labs, and industries, internships. And you can search through this and see if there is something that interests you. Also, I strongly encourage you to join LinkedIn. You start clicking on follow some of the people doing quantums, and more people will show up, and you will see a lot of opportunities there. But also it's a good source to read about recent developments in quantum, because things are developing so fast, and in order to keep up with this, you really need to read every week something new is coming. So it's a good source of keeping up with the quantum. But the bottom line is the take-home message number 2, we need you. You are the people who are going to bring technologies to real world and applications. And I hope I translated to you some presentations that there are jobs in this field in national labs, in industry, in university, and you can start as early as a high school bachelor student or master student or even PhD. But we need you to drive this field further. And now I'll talk very quickly, because I'm out of time as always, on a workforce development at MTSU. So we started really from zero in 2022, but we launched the Quantum Initiative in 2022. And this fall, we launched the Quantum Center. Quantum Center was launched based on the funding we got. So we got 6 National Science Foundation grants and 2 Department of Energy grants, totaling around $9 million. And we also built, I think the signature program of our program is that we are not doing this by ourselves. We are bringing smaller institutions to the table, because we know otherwise they will never have opportunity to participate. And we extended our research program and as well as educational program. So over the last 2 years, I was able to hire 3 different faculty: quantum materials, quantum sensing, and just last week we hired faculty from Virginia Tech on quantum algorithms. We have 4 postdocs. I didn't put one more picture, including one from Ukraine, Maria Karabin. Our research focuses on quantum materials, quantum computing, quantum control and sensing. This is Fu having fun building his quantum sensing lab. And about now education. So education is built on a different level, because quantum is very new. We basically do also what Kharkiv is doing right now too. We go from high school students, even middle school students, we do summer camps. We do workshop in schools like yours, and I find the summer camps and schools like this are very useful practical mechanisms to inspire interest and encourage students to pursue the programs in quantum. This is Connor. He just built this ion trap model for high school students. So this just shows how trapping of ions is happening. He's going to show this today, this afternoon. I have the event. He's going to show this. By the way, this was done based on the development in the group of Roger Melko. And I think he's a good friend of Kharkiv, I believe. At least I met him a few months ago, and he mentioned you guys. So once we recruit students from high school, we develop undergraduate programs in quantum. So our university was the first in Tennessee to launch quantum concentration for undergraduates. And as I mentioned before, you have majors from computer science, physics, math, bio, chemistry, and from different institutions. One important thing that is also important for your training is to go and do internships. We have, this is Abdul Khalik. He has done internships in AWS, and it landed him now a real job. So he has a job offer. He graduated 2 weeks ago and has a real job offer with this company. So doing hands-on experience in internships is very important. I mentioned Oak Ridge. So last year we got $2.2 million grant from Department of Energy, where the goal is to work with Oak Ridge National Lab on quantum materials. This is a great opportunity to work with other institutions in Tennessee. So we ran our, like you have school, we did fall school in Nashville. We had 100 participants from 8 different institutions with multiple hands-on activities, including AI, quantum computing, and many-body simulations. I also want to mention this slide because in addition to classical university programs, like you take classes, there are so many resources online, and because things are developing so fast, I do encourage you to go online, go to YouTube, look at webinars. IBM Qiskit YouTube channel is very active. Participate in different hackathons. This is a great way of get educated in quantum. And maybe I should skip it, but we also have STEM with Ukraine program. That program works for scholar exchange, collaboration, mentoring. So we have our first program in STEM with Ukraine was to runs the Introduction to Quantum Computing class in Ukraine. So we had participants from 12 regions of Ukraine. So I think that was a very enjoyable experience for me. We had also remote research opportunity for students from Western Ukraine, but also from chemistry department. Dr. McDougall collaborated with Yevhen Krechko from Kyiv. And we also have welcomed two scholars from Ukraine to visit United States. They traveled to different institutions, raise awareness, build collaboration. And last fall, we had leadership in academia course. I think we find that there is need for community building, collaboration, and real connection between our countries and different institutions. So with this is a summary of my talk. I'm so sorry I took 6 minutes longer. I hope I convince you that quantum is interesting. It is time for you to get inspired and act on your interest. There are so many opportunities across different spectra, and this school in Kharkiv provides you this opportunity. You will have faculty from universities, but also from national lab and industry providing you opportunities and telling you about what is up there available. So don't be shy, get involved. Get educated. You have great program in Kharkiv. And if you have any questions, please ask me. And thank you very, very much for having me. And слава Україні!
Слава. Дякуємо, дуже дякуємо, пані Ганно. Конце на Америку, так. У нас, на жаль, немає питання, бо це віконце обмежено часом до 18 години. Ми б хотіли б ще випускниць трохи. Але якщо можна нам надіслати ці слайди, ми б ще тоді дали б учасникам, і вони могли б написати свої питання, якщо потрібно, тоді емейлом до вас.
Добре, дуже добре. Вибачте, що я пішла over час.
Ні, все гаразд. Це просто організаційні обмеження, які ми дізналися півгодини тому просто.
Добре.